Now that we've introduced mechanical energy and our potential energy functions, we're describing our systems differently. We talk about states, we talk about the potential energy of that state, we talk about the mechanical energy of that state. Remember, we're always referring to a reference state for our reference potential. But in one dimension, what we have is that the potential energy, say in some final state, minus the change in potential energies from some initial state, was that integral x final of the x component of our, I'm going to put C up there for conservative force, dx. And now we can, so the potential energy difference is the integral of the force with a minus sign. Now let's look at a fundamental theorem of calculus, which tells us that any time you take the difference of a function between two endpoints, then by definition, that's the derivative integrated with respect to the dx. So when we compare these two pictures, this is a math here. This is our physics, how we define them. That when we compare these two pictures, we see that we can recover the conservative force by taking the derivative minus the derivative of the potential function. Here, force does not depend on any reference point. And when we differentiate a constant, that's 0. So this is independent of the reference point. And this enables us to, when we think about the potential function and its first derivative, then this tells us about forces. Let's look at an example. Suppose, again, we look at our spring potential, where we're talking about the potential energy function of a spring, where at our 0 point, where it was unstretched, was our reference point. And if we plotted this function, so let's plot that function. So here's u of x versus x. Now we can talk about at any given point. So suppose we're at a point here. Maybe our energy has some fixed value. Then the slope at this point is equal to du dx. And the force is minus that slope. So here you can see that the slope is positive. So the force is negative. So I can write fx like that. So here fx is negative. So our actual force is pointing inward. When we're on this side of the potential function, my slope is negative. So the x component of the force is positive. So my force is pointing everywhere on this side back to the unstretched length. So knowledge of the potential function, also by knowledge of its first derivative, gives us information about the force at any point, any state that the system is in. So when we talk about potential, implicitly, we also know what the force is. And the potential function is enough to tell us what the force is at any point. And let's just check for this simple case. This is minus du dx. When you differentiate that, you get minus kx. And we know that's the spring force. So this is why we're subtly shifting our focus to our state, our function u of x, and its first derivative. Let's consider a system in which there is no non-conservative work, and there's a potential energy associated with forces in the system. And for an example, let's write our potential energy like a following. We'll model some system by the following function, bx cubed. And we know that our definition of force is that it's minus the change in potential energy. So if we differentiate this, our force is a function of x. And because of that minus sign, you always have to be careful when you take that type of derivative. We get, as far as the force goes, 2ax minus 3bx squared. Now, we ask ourselves, where does this force vanish? So if we look at the 0 points for the force, we can see immediately that there's one x equals 0. The other one, if we set 2ax equal to 3bx squared tells us that we have another 0 point at 2/3 a over b. Now, let's also, for our example, just put some numbers in for some simplicity. Let's write this as 4 joules per meter squared for A. Why do we have meter squared? Well, the units of potential energy are joules, and we're multiplying by x squared. And so you can see that B, also, we're going to write as 2 joules meter to the minus 3. And if we put those numbers in, we can see that we'll get 8 over 6. And 8 over 6 is just 4/3. And that will be in meters, where the other 0 point is. So that's nice, but we'd like to know some properties of these 0 points. If we had a particle that we started with some energy at one 0 point, where would it go? What would it do at the other point? So in order to understand a little bit more detail about these 0 points, let's make a plot of our potential energy u of x versus x. Now, to begin with, we want to ask ourselves, how does this function behave? And for big values of x, the x cubed piece will dominate. And if we're positive x, we dominate with a negative value for potential energy. So our potential energy function goes off into negative infinity as x goes to infinity. Now, on the other side of the scale, the x cubed term will dominate for negative values of x, but this term is negative and that's negative, so up here it will go off to infinity in the positive direction. Now, where are the zeros of the potential function? There's one, obviously one, at x equals 0. And with these values, it's not 100% obvious immediately, but 4x squared minus 2b x cubed, if you set x equal to 2, 4 times 2 is 8, b 2 times 2, 4 times 4 is 16. If b is 2 and x is 2, that's 16. So we get a cancellation at x equals 2. And so we have a point up here. I'm sorry, that's our 0 point at x equals 2. Now, we said that the force at x equals 4/3 had a 0. And so if we plot this function, it's going to look something like that. Now, let's focus on these 2 points right here, where our force is 0. Remember that this is minus the slope. And so we can see immediately that these 2 points have 0 slope, and so the force is 0 there. Notice potential energy always depends on a reference point, so whether the potential energy is 0 or not is not crucial. But the physical fact that the force is 0 there has physical meaning. So here, this is one of our points, xx, f of x is 0. Now, what is the property of this point? Well, suppose we ask ourselves, if the particle were just displaced slightly from this position where the force is 0, which way would the force point? Well, in order to answer a question like that, we can look at the slopes on either side of this 0. So over here, the slope is negative, but the force is minus the slope, so f of x is positive on this side. And so if a particle is displaced a little bit from this 0 point, it moves off to the right, and it will continue to feel a force in this direction, and so it will move away from this 0 point of the force. Now, on the other side, we do the same type of argument, and over here, the slope is positive, but the force is negative. So again, what we see on this side, the particle will move away from this 0 point. And so if our particle just started there and it had a little bit of kinetic energy, it would move one way or the other away from that point. And so we call this an unstable equilibrium point. And that's an abbreviation for equilibrium. Now, what about this 0 point over here? Well, we already know that as the particle, if a particle is on this side of the 0, it feels a force this way. But what if our particle were on this side? Well, once again, we analyze the slope. The slope is negative. Force is minus the slope, so it's positive. So everywhere on this side, the particle is getting a restoring force back to equilibrium. And so if we displace this particle just on either side, if it doesn't have enough energy to get over this point, then the particle will stay around this area. And that is why we give this point the name of stable equilibrium point. There's even a little bit more that we can learn about our energy diagram. And I like to just clean this diagram up for a little bit of a second because I want to work in this area. Suppose our system, because the work non-conservative is 0, tells us that the mechanical energy is constant. Now, we don't know how much mechanical energy our system is. That's a constant of the system. But let's just suppose that our mechanical energy is written like that. And we'll just clean up a little, give ourselves a little space. So here's the mechanical energy of the system, and that's a constant. And now we can talk about 2 more special points. A point over here. And at this point, let's just think about what our mechanical energy tells us. This is a special point, but let's begin with one right here. If our particle is at this location, then this represents the potential energy, and the difference between the energy and the potential energy is the kinetic energy. So this here represents the kinetic energy. And now we can ask ourselves, what would happen to the energies as our particle is moving? So if we start right here, the kinetic energy is 0 because all the energy is potential. And as the particle starts to move, let's say it has a little bit of energy, it starts to move in this direction, then the kinetic energy starts to increase until we get to this point where the kinetic energy is maximum at the stable equilibrium point, where the force is 0. Now the kinetic energy decreases because, remember, it's now going against the force. This side, the force was pointing in that direction. Here, it was in the other direction. And until we finally get to this point where, again, the energy of the system is equal to all potential energy, and so there is no kinetic energy. So I'll call this point A, and I'll refer to this point over here. My diagram is getting a little crowded as B. And those points A and B are what we call the turnaround points. And they represent the places where the kinetic energy at XA is equal to the kinetic energy at XB, which is 0. Now, the last thing that we like, there's a lot of information, as you can see, contained in these energy diagrams. And the last bit of information that we'd like to ask ourselves is, what would happen if instead of confining our system to this area, we increased our mechanical energy so we're up here? And let's just follow qualitatively the motion of a particle that begins, say, over here with a little bit of kinetic energy and potential energy. And if the particle starts off with a velocity in the positive x direction, then it's going to move in this direction. And you can see the kinetic energy is increasing. Here we have a maximum amount of kinetic energy. But notice that over here, the particle still has some positive kinetic energy. And so it can get over this hill. And when it gets to the other side, the force was in the positive direction. It increases its kinetic energy, and it goes off to what we're referring to as infinity. So one analogy that people like to make is to understand the motion. Think of a marble that's rolling down a hill. And this is just a metaphor for this potential energy function. As the marble rolls down the hill, it gains kinetic energy, it loses potential energy, it comes maximum at the bottom of the hill. As it goes up the hill, it still has enough kinetic energy to get over the top of the hill and to start to come down the other side. And of course, our particle can never get to the speed of light. So our model has to break off at one point.